You ever go to a grocery store in a college town and see ping pong balls for sale in the aisles and wonder, why ping pong balls? Let me tell you why. College students love to think about and experiment with trajectories, especially uneven trajectories. There's this game called beer pong where you take a ping pong ball and you throw it into a cup. And I think if you get it in, the other person does something, but if you miss, you have to drink a beer. I don't really know the point of that part. The fun part really is thinking about your trajectory and trying to get it in and win the game. So we're going to do a problem sort of about this game called beer pong. All right, let me see. I got to get one in here. I made like 5 in a row when we were setting up. Okay, so here we go. So we're going to solve this problem, beginner's beer pong. You throw a ping pong ball from about half a meter high at 3 meters per second, right? And at 35 degrees to the horizontal, 35 degrees above, and into this 20 centimeter, 0.2 meter high cup. So we want to figure out, for this one, how far away is the cup, if all that happened. So we could think about the trajectory. We know it's going to look something like this into the cup on whatever the 7th try, whatever it was. So this is an uneven trajectory because it starts at one height, ends at another height. I usually tell you to solve these problems by writing the position in x and y as a function of time and just solving it. And in this case, because it's uneven, that will actually lead to a polynomial you'll have to solve. You'll have to find the roots of a polynomial. So actually, for these kinds of problems, it's better to not do that. For these, it's actually better to find the apex here and think of it as 2 problems. One is half of a uniform trajectory to go up, and then another uniform half trajectory to go down. And to just think of it as 2 problems, 1 and 2. And then whatever you're asked usually is easier to break it into 2 parts this way. So that's how we're going to solve this problem. All right, so start as you typically would with these. You want to break your v initial into components, right? So we want to say vy initial is the 3 meters per second times, let's see, the y will be the sine component. So 3 sine of 35 meters per second, which is 1.72 meters per second. All right, and then we need the x. The x initial is 3 times the cosine of 35, which is, of course, this component, the speed it's going forward, 2.46 meters per second. The horizontal is larger because I didn't throw it at that big of an angle, 35 degrees. So now, to solve this, really you get the idea. What we know is we know the x component stays constant. We just need to know how long it's in the air. Right? How long does it go up, and then how long does it come down? So let's see. So the hang time in 2 parts. And in this case, we're not even going to use the range or the projectile formulas. We're really just going to calculate it. So this part, T1, T1 is simply this velocity, this vertical velocity, 1.72, being reduced to 0 by gravity. So it's 1.72 over 9.8. So it took it about 0.176 seconds to go up. 3 meters per second might have been a little bit of an exaggerated throwing speed for beer pong. So now we need the time for the second part of the trajectory. So we look at that, and it starts actually at a height we don't know yet. It starts up here. So let's figure out how high it got for the second part. That would be, the quickest would be v final squared equals v initial squared plus 2ad, because we're accelerating for a distance that we want. So final is 0. Right? The final velocity squared is 0 in the y direction. The initial velocity is 1.72 plus 2, and the a is 9.8, and then that's the d we're looking for, and it's minus because it's down. Right? So then we'll get d, how high it got above that, and if you work that out, you get d equals 0.151. So now what you know is that the ball has to fall from a height of 0.5 plus 0.151. Fall straight down. How long does it take? Then that would be, let's see, the final position is 0, is the initial position, which is 0.5 plus 0.151, which is 0.651, plus v naught t, which is 0. There's no initial velocity when you're just sitting here falling down, minus 1/2 gt squared, minus 1/2 9.8, and this is t2 squared. Okay, so we bring this over here in the 2, and you divide by the 9.8, and you take the square root, blah, 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 and you get T2, if you work all that out, is 0.3034 seconds. T2 is 0.3034 seconds. So the time for the whole thing, T1, T2, we could call that the hang time. We've basically solved for the hang time for this uneven trajectory. And it's just the sum of those two, 0.176 and 0.3, and it's about 0.479. But we weren't asked for the hang time. We were asked for how far? The range, in this case, the range for an uneven trajectory. So to get that, we just have to figure out r is simply d equals vt, right? So it's how v, the x velocity, 2.46, in the x direction, 2.46 meters per second for 0.479 seconds. And then you get how far away was the cup? 1.18 meters. 1.18 meters. So about a meter away.